Looking at what are we looking at here? These curves are what curves they are. Let's just remember where we stopped on Wednesday. What kind of failure mechanism were we studying last? Yes, fatigue, exactly. And these curves are called, someone else, a brave volunteer. What are these curves called? SN curves, right? We call these SN curves, which is like a stress versus number of cycles curves. And they are useful for fatigue, for making sure that we are designing the structural member or part such that we are in the safe zone, considering the fatigue behavior of the material that we are dealing with. So take a look and try to remember some of the expressions that we talked about: fatigue limit, fatigue life, and the fact that, for example, steel and aluminum, they have very different behavior. Aluminum the strength is continuously decreasing. Steel reaches the fatigue limit, which is a nice thing to have if you have repeated loading. So this curve, which also appears in your homework number 3, which is already posted on Canvas, 4 problems only. It's not very long, but it's already posted. It's on fatigue. It shows the SN curve. So S is for stress, N is for the number of cycles. This is what these curves are called. SN curves for different materials. And I thought it's a good idea for us to warm up with an example. So a cylindrical brass bar, you see the exact composition, which can help you find it in the graph that you have in the previous slide, is subjected to axial tension compression with reversed cycling. I hope you remember this reversed cycling, which means that basically you have sigma max positive, sigma mean negative, and the ratio is -1. It means that you have the same compression and tension and it cycles. And the load amplitude is 10,000 Newton. That's the load. And you want to find the minimum bar diameter such that the fatigue life will be no less than 10 to the 7 cycles. So N is 10 to the 7 cycles. This is the number of reversed cycles. So what you need to do is go back. First, find out the curve which corresponds to this material, which happens to be this green curve that you have here. And you want to have the fatigue life of 10 to the 7. So you want to see what would be the maximum stress amplitude that the material can tolerate without going through fatigue failure at 10 to the power of 7 cycles. So this is, you go here, you go and read it, and this gives you the maximum stress. Let's say 120, it's about 120 megapascal. Why I say maximum? Because if I have a little bit more than 120, then I have fatigue failure. Remember, above the curve is unsafe. Underneath is safe. So that's why this is the maximum stress at that fatigue line. Now, so from the graph, we find out that the maximum, so it is a stress amplitude. This is maximum stress amplitude. Sorry. It's about 120 megapascal. And look here, since the loading looks like that, the maximum stress and maximum and the amplitude would be the same. So this is also the stress amplitude. So there is one more thing that we have to be careful about, and that is the factor of safety. So what do I do with factor of safety now? Now I want to design the bar. I know the maximum stress that I can apply without having fatigue failure is 120. What should we do next? Can I design for 120? No. What would be the safety factor if I would design for 120? 1. And that's normally not acceptable. So exactly, I'm glad that this is clear. So we have safety factor of 2.5. So we need to actually design so this is basically, you can think about this as this 120 as fatigue strength. You know how we had before, like maximum tensile strength for the little beam that you also had in your homework? So here this is fatigue strength. And we divide it by 2.5 to get the design stress. I actually don't have the number, so if someone can calculate the number, I forgot to say. How much? Thank you. And now the rest is very easy. This is a tensile compression. So you have a bar, cylindrical. It's going through a cyclic loading. Pay attention, I put the arrows on both directions. It means that you have tension, compression, tension, compression. So the load is 10,000 Newton. We know that. So the stress would be just load over A, and you want this to be less than 48 megapascal. So this is 10,000 over this is the area written in terms of diameter, less than 48 megapascal. It is useful to know that megapascal is the same as Newton per millimeter squared. This is a useful thing, because if you have the load in newtons and you have here megapascal, if you calculate the diameter here, it will be all okay, and it will be in terms of millimeters. Does it make sense? It's useful to think that, to remember that these are the same thing. So if you solve for this inequality, you will get some value for the minimum diameter, and that's the design you are looking for in millimeter. I kind of remember the number, but I forgot to take it with me. So please. So let's look back again what we did. So from the fatigue life, we need to have a center to get the fatigue strength that we would need. And then that would be like the fatigue strength, but if you apply a safety factor, you have to design for something smaller. Here, safety factor was 2.5, so we get 45. And then the rest is just to say a stress should be less than a strength divided by safety factor, and then you get the minimum diameter. Any questions? If you are done and this is obvious to you, look at the next example. That is actually from an FE exam. Just copied and pasted. It's a fun problem, really fun problem to study. The other one with the help of your neighbors and talk about it, see how to approach it. So the graph is in megapascal. It's a stress in megapascal if the shadow makes it a little bit hard to read. So this is a stress in megapascal. I'll be looking for 3 correct answers. So it's common that you see the x-axis in logarithm scale. So please don't be confused. If it says 5 and it is in logarithm, that means 5 is 10 to the 5. And 6 is 10 to the 6. That's it.
Something like
When you get n, just calculate its log. Then you get a number. So the x-axis is the log of n. Just when you calculate n, take the log. The stress is one cycle of what makes fatigue different from the other mechanisms is repetition. You take care of that by looking to see where you are. I've seen two correct answers. Okay. So the first thing is we can calculate the stress, and don't be confused. Every passage of a car makes this much stress. You don't have to multiply it by the number of cars or anything. The whole point about ascent curve is that you look at if you have so many repetition of the same thing when it breaks. So the stress here is not cumulative. It's just a stress for the passage of one car, for example. And then to get n, I saw many correct answers, so I guess you all know how to do it. So it is like 50 car per hour, and then 24 hours per day, I would say. And then 365 most years, day per year, times 5 years. Why do I write it like that? Because it's kind of, you see that it at the end gives you the number of cars. And I think it's around 2.2 times 10 to the 6 cars, if I'm not mistaken. Yes. And if you take the logarithm of this number, which is not hard, it's just you press logarithm on your calculator or something, you should get a number which is about 6.3 or 4. And then all we need to do is to basically look up this number and see, okay, if you go here, this level of stress, these many repetitions, and now I guess then we have to decide what material would fail, what wouldn't fail. The point is above copper and cast iron. That means that they both fail. If you look at this number, the cast iron will fail at much lower stresses here, and copper slightly lower. So it cannot tolerate so many repetitions of the cars. The two good materials are steel and aluminum. And then you have to. So this was an empty question. Kind of. I thought it's a fun question to look at. If you have more cycles here. But this is not the question. You know this is what you want. Aluminum is always much cheaper. You always don't have money to buy steel. Of course. Any questions? Objections? Okay. A few more things about fatigue crack propagation. So one thing which is very important is the rate of crack growth. So here A is the size of the crack. As you remember, if it is an internal crack, this was 2A. If it was a surface crack, it was 1A. So the growth rate, dA over dN, so that means how fast the crack grows with respect to the number of cycles. That's why I call it growth rate. It has a typical behavior like that. So in the beginning you have a small cracks and it is fast. Then you have a stable region which is called Paris region. And then it becomes very fast and you have fracture. The relationship between fracture toughness and crack growth is during the stable regime is what you see here. We don't do much with this here, but if any of you at any point of time had something to do with fracture, you are going to use this formula to see how fast a crack would grow. And what is important for me to know is that when you look at this equation, you see that if you have higher stress, because higher stress means higher delta K, so you have faster crack growth. So if we have higher stress, we have faster crack growth. And then as the crack gets longer, it grows also faster. And sometimes, if you have faster loading. So the loading rate is faster. And the crack also can grow faster. This depends on the material a little bit, but these are generally true statements. So typically after the fracture, people do like forensic investigations if they want to understand the fracture propagation, and they find out where the crack has nucleated and how it has been progressed. And then you can also measure the crack growth from these patterns that you see here, how closely they are located to each other, etc. It tells you how fast the crack has grown. So it's important to kind of have an idea what makes a crack grow faster. If it is larger, if you apply more load, and if you apply the load faster, typically these are some of the driving mechanisms. Now, after telling you all these values about having a little crack and having fracture, I think it's also time to say, what can we do about it? What are the things that we can do to make sure that we don't have failure, fatigue failure? A very important graph that I want everyone to understand is this one. Here we are looking at SN curves, and look at these different colors, slightly different shades of red. So if you have the mean stress is more tensile, everything gets worse. I told you why last time, because it's much easier to grow a crack when you have tensile stress. So why I say it is worse, look at the safe region. The safe is under the curve, so it's very small. As the mean stress becomes more going towards compressive stress, then you see that the safe area is increasing. So what that tells us is that if we find a way to, if the material is going through cycles of tension compression, if we find a way to increase the mean stress such that it doesn't go through tension a lot, we can improve the fatigue level. We can increase the area under the curve. So we are less likely to be in the unsafe region. Again, so one way to improve the fatigue life is to make sure that we are not always in the tensile region. So you try to kind of pre-stress the material with compression. You pre-stress it with compression, so when it goes through the cycles, the mean is compressive or zero. It's not negative. Because as you can see, when you increase the mean towards zero or compression, you increase the safe area. And this is what we want as engineers. Is the concept clear? And of course, another thing is the more stress you have, it is worse. So if you look here, as you are looking, when the stress is increasing, then you are going to have less and less number of cycles, as you can see in the SN curve. That's something that we can't do much about it if we have an application with a certain stress. So how do people generate compressive stress in material? One way is you basically hit the metal surface. So it's called shock heating, as you can see here. So you basically put the near surface region in compression by shooting like balls over to make it to put it under stress. This is a physical method. Another method is a chemical method. So you place your material inside a chamber and you do carburizing, which also creates a stiff layer near the surface, which puts the material under compression. So again, your purpose is actually in that graph. You want to increase the mean stress towards compression rather than tension. And something else that I already told you about is you want to make sure that you don't design anything which looks like that. You don't want anything which is very sharp. You want to have a smooth transition in your design. So these are some of the things we can do to ensure better fatigue life. So I guess those are the same. Also, it's important to note that the curves that you would get in the lab, they are not going to be just 1 point making a nice figure. You are going to have these kinds of distribution. One question that may arise is, what if you have different levels of stress at different repetition rates? What if, for example, you want to design a girder and you have, let's say, trucks of different kinds, each one of them associated with a certain level of stress and certain number of repetitions? How do you design for fatigue control? The way to do it is you basically look at the number of repetition at each stress level and divide it by the failure, by the fatigue life at that stress level. And make sure that the summation is less than 1. If it is more than 1, you have failure. Let me show you in an example, it would be easier. So here, we want to see if you have this SN curve, if this material is going to fail. We know that at 3 KSI, so here stress is in KSI, we know that at 3 we have 900 repetitions. At 5 KSI we have 50. And looking at the curve, at 3 KSI, we know that the fatigue life is 10,000. At 5 KSI is 500. So the question is, would this material fail or not? The difference between this and the previous discussion was there we only had one element stress. Now what happens if we have one? So what we have to do is, using the linear view, to look to see, okay, number of cycles to fatigue life at each stress level, we calculate it, and then sum them up, make sure that it is less than 1. So let me show you the equation. So this is number of repetitions applied at each stress level. This is the fatigue life at the same stress level. So in this example, this will look like this. So it is, we want to calculate number of, let me use the same notation, Ni over, let's say Ni. It's better to write this with a small n here to make things. So here we have just 2. So it would be N1 over N1 plus N2 over N2. And this is number of applied cycles. This is the fatigue life. So here is at 3 KSI. And 2 is at 5 KSI. And once we set this up, it's easy to calculate. So then we say, okay, we have 900 over 10,000 plus 50 over 500. And if you calculate it, it's something about 0.19, I think. And this is less than 1. So if you have only one stress, you would check one of these if this is smaller than that. If you have multiples, you need to look at the summation of the ratio and make sure that the summation is less than 1. It's simple, but okay. So it seems that we do have time to do the So let me explain the pop quiz. It's not the same as the pop quiz is from the materials that you have just learned. You actually can talk to your neighbors. It's more like an attendance than the quiz. But of course you have to try to solve the problem. Yes, we can also use your notes. So with that, we are kind of we time dependent with the elasticity from one day or another. It looks as if I need to push the exam number 1 a little bit to the later date. I send you an email and make sure. How many are dancing in prom? Does everyone make sure you write your name? So you see, failure does not. Okay. Does everyone have the quiz? Is there any extra copies from So, these are from the same material, and So what you need when you want to compare them, how do we compare them? What you want to see is what is the stress amplitude and what is mean stress. I showed you that if the mean stress is more tensile, things get worse. Also, the larger the stress amplitude is, things get worse. So what you want to do is for every specimen, you want to calculate a stress amplitude and mean stress. If you don't remember what these are, no problem. Look at your notes. That's the exact point. You can talk to each other. You can ask me questions. You can look at the notes. If you don't know where to start, do that. Calculate the stress amplitude and the mean. The stress amplitude is half of max minus mean, and mean is half of summation. So if you have larger stress amplitude, you have your fatigue life will be smaller. And if you have sigma m, which is tensile, again your fatigue life